In today's experiment, we're going to determine the molar volume of oxygen. Molar volume is defined as the volume occupied by 1 mole of gas. It's usually given at STP. In our experiment today, we'll be generating oxygen, and we will be determining both the volume of oxygen generated and the weight of oxygen which has been generated. And of course, from the weight, we'll be able to determine the moles of oxygen generated. And then from this information, as you can see by this equation, we'll be able to determine the molar volume. The reaction which we'll use to generate oxygen is the thermal catalytic decomposition of potassium chlorate. We'll use manganese dioxide as the catalyst, and this mixture of potassium chlorate and manganese dioxide upon heating will give off oxygen gas and leave behind potassium chloride. Now there are two things to remember about this reaction. First, all of the reactants and products, that is the potassium chlorate, the manganese dioxide, and the potassium chloride, all of those are non-volatile solids. The only thing which will escape upon heating is the oxygen gas. Therefore, if we have a weight of the container and all of these materials before heating and after heating, the loss in weight is going to be equal to the weight of oxygen generated. The other thing which we're going to use in today's experiment, particularly when we calculate the purity of the potassium chlorate, is the stoichiometry of this reaction. Please note, 2 moles of potassium chlorate will generate 3 moles of oxygen. With all this background material in hand, the experiment itself can be summarized in 4 steps. First, we'll weigh out the potassium chlorate and the inert materials such as the catalyst or any impurities which may be in the potassium chlorate. The potassium chlorate itself is the only thing, though, which should lose weight because it's going to be heated and generate the oxygen. If we, for example, have a wet test tube, the water will vaporize, but we will think that we are generating oxygen. So please do not use a wet test tube in this experiment. After we have weighed out the potassium chlorate, we will heat the potassium chlorate and collect the oxygen. The oxygen is collected over water, that is collected by the displacement of water in a flask, and we will then measure the volume of oxygen which we have generated by knowing the weight of water displaced in the flask by the oxygen which is generated. From this weight of water and the density of water, we will be able to calculate the volume of water which was displaced, which is equal to the volume of oxygen generated. And finally, of course, here we are, that the measured weight loss in the test tube will be equal to the weight of oxygen generated, which we can, using the molecular weight, convert to the moles of oxygen generated. Well, let's see what the experimental setup looks like. Here's the apparatus that you're going to be using today. You will get from the stockroom these 2 test tubes, there's one of them here, and you'll clamp it in place. Now when you clamp it in place here, make sure that the clamp you have does not have rubber pads on it, because when you heat the tube, if the rubber should melt, it'll change the weight of the test tube and therefore give you bad results as far as the weight of oxygen generated is concerned. Then you will get this tubing. You will set up the tubing in this manner. This part gets clamped in place over here, the top of the test tube. The other end goes to the side arm of your reservoir. This is a suction flask which uses a reservoir here. When you're putting tubing rubber tubing on glass tubing, make sure that both of these are wet, and then the tubing will slide on much easier. And finally, what you'll do is you'll put in this tube, which will lead from the reservoir here into your collecting flask. Your collecting flask is a 125 milliliter Erlenmeyer flask. To set up the collecting flask, you merely fill this up with water completely, so that, and then when you put it out of water, do not take the opening out of water, and just hang it up then so that the opening remains underwater. Now your flask is completely filled with water, and it'll be only the oxygen which displaces this. Is concerned. We won't go over all the details, but there are a couple of words of caution. Please use the same balance for all 4 weighings in a test tube. As you put material in or you weigh the thing after it's heated, use the same balance for all those 4 weighings. If you want, you can use another balance for your second test tube, but use that balance for all the 4 weighings. Now, in weighing here, there are a couple of other precautions which we'll use. Make sure that when you put things on the balance pan, you use these little slots in the balance pan to hold your test tube. And when you put your test tube on, make sure that the test tube is on in such a position so that it does not tilt the pan and give you bad results. Make sure that you have the pan level when the test tube is on. You close the door. Then during the weighing and before the weighing, check to see whether or not the ends of the test tubes or the bottoms are touching the side of the balance case or the bottom of the balance case. The test tube itself must never touch the balance, otherwise you're going to get a wrong result. Finally, when you're putting this tube on or taking this tube off the balance, make sure that the beam is arrested. That is, on the side here, you make sure that that lever is turned off. All right, now we're all ready to run this reaction. First thing, double check to make sure that all of these connections here are tight. Then you take the outlet from this surge bottle here and put your finger over the top here so that you don't get any water in there, and then slip it underneath into the flask here. There'll be some air which came out, but that water which went into the tube will be blown out when we heat this up. Now we start heating it. Heat it fairly gently at first. The first thing that's going to happen, you can see that there are bubbles coming up into the flask there. That's because we're heating air and the hot air is expanding. So far we haven't generated any oxygen yet. The bubbles that you see coming into the flask over here, these bubbles are all just from heating the tube and expanding the air. Now we're getting melting of the potassium chlorate, and the manganese dioxide is starting to catalyze generation of oxygen. There we go. Now we're really generating the oxygen at a reasonably rapid rate. All that water that had originally gone into the tube, rubber tube, is now being blown out by the oxygen which is generated here. And here we go. The tube has become solid. We can stop the heating at this point and let the whole system cool. When the system cools, the air which came into this flask due to the heat expansion here, will be drawn back into the surge bottle and into the test tube here. When the system has cooled to room temperature, what you simply do is you remove the delivery tube, take your rubber stopper and stop her tightly so that there is no loss in gas or pressure of this tube, and then you can take it to make sure it's tight so you don't lose anything in here, then you can take it to the leveling tank. Let's take a close-up look of that heating process. First of all, though, make sure that all the material you put in this test tube is at the bottom here, not along the sides. Now let's do the heating here. Start the heating. And as we pointed out before, the first thing that happens is the tube gets hot and there will be some gas due to expansion. Then you get melting, and the melting material will generate the oxygen. And finally, it will re-solidify, and that's the end of the reaction. Having collected your oxygen, you will now go to the leveling tank to bring the pressure of the gas inside your flask to atmospheric pressure. We have our flask still tightly stoppered. What we must do at this point then is to put it underwater. We stoppered it underwater and we must unstopper it underwater, and we take out the stopper upside down so that the mouth of the flask is underwater, therefore no gas escapes. As I am holding the flask, the pressure inside the flask is less than atmospheric pressure. If I push it down into the water, now the pressure of the gas inside this flask is above atmospheric pressure, and if I should raise this just to the level of the water in the tank, then in fact the pressure inside this flask will be exactly atmospheric pressure. Once we have the pressure inside this flask exactly at atmospheric pressure, we simply have to put a stopper over the bottom here and then just raise it up out of the tank, and that's the end of the experiment. Here it is once again. They say when we get the two levels, the level inside and the level outside, and we know the pressure of the oxygen inside the flask is atmospheric pressure, we simply cover the mouth of the flask with this large stopper, just bring it out of the thing, and then we can release it to atmospheric pressure. At this point, this is the volume of oxygen which we've generated here, and we will be able to measure that. You finally weigh the flask and the remaining water. Well, except for a couple of weighings and a temperature measurement, you've seen the entire experiment. Of course, you'll be running a duplicate run as well. Well, how are we going to use these data to determine the molar volume of oxygen? Remember the definition that we saw before, that the molar volume is equal to the volume of the oxygen divided by the number of moles which occupies this volume. Let's look to see how we can convert our data into the volume of oxygen. To determine the volume of oxygen generated, we're first going to measure the weight of water displaced by the oxygen. We have here the flask in which we had collected the oxygen. We had weighed that, and so we'll have the weight of the flask with the remaining water. Now if we fill this flask up completely to the top, we'll have the flask, the weight of the flask filled with water. So we'll have these two weights represented by the two flasks here. The difference in these two weights will tell us how much water was displaced by the oxygen. So we will know the weight of the water displaced by oxygen. The weight of water displaced by oxygen divided by the density of water will give you the volume of water displaced by the oxygen, or in other words, the volume of the oxygen itself. To find the volume of oxygen at STP, we can use this familiar form of the ideal gas equation. This, for STP calculations, takes on the form where the 760 millimeters here represents standard atmospheric pressure. 273 degrees Kelvin is the 0 degrees centigrade, and this then would be the volume at STP. The only problem that we are left with is the pressure of the gas, and we'll see how we have to correct that. When we took our flask with the collected oxygen out of the leveling tank, it was the gas inside was at atmospheric pressure, but there were actually two gases inside, the oxygen and the water, each one of which was contributing its own partial pressure towards the total pressure, which was the atmospheric pressure. The water vapor in the flask at that time was probably the vapor pressure of water at the temperature of the water, and so we will have to subtract that. We'll look that up in a handbook and subtract that from the atmospheric pressure to give you the pressure of the oxygen, which you'll then use in this ideal equation that we just had just a second ago. Having determined the volume of oxygen generated, we are only left with determining the number of moles of oxygen generated, which we of course can find out if we know the weight of oxygen generated. The weight of oxygen generated is of course given by the difference between the weight of the test tube before heating and the weight of the test tube after heating, so that we can now determine the weight of the oxygen generated, and we know the number of moles of oxygen generated. Having calculated the volume at STP and also the moles of oxygen generated, you'll now be able to calculate the molar volume of oxygen at STP. Also, from your data which you've collected, you'll be able to calculate the purity of the potassium chlorate you used. Well, at this point, I think you should start the experiment.